My name is Walid Krishen, and I will present the paper on sampled metrics for item recommendation. This is joint work with Stefan Rendle. Evaluation metrics are used to compare the performance of two recommendation algorithms. Because the number of items to recommend can be large, it's become common to compute the metrics on a random sample of items. In order for this procedure to be meaningful, a desirable property is that, in expectation, the order of the metrics is preserved. Our main result is to show that this is not the case for many common metrics used in recommendation, including precision at k, recall at k, average precision, and NDCG. For this reason, we believe it is better to avoid sampling during evaluation if at all possible. When that is not possible, we provide some correction methods to improve the quality of the estimates. Let me start by defining evaluation metrics and sampling. We consider the following setting for item recommendation. Given a query X, the recommender algorithm is used to rank a set of n items. Then the items are presented to the user, who chooses a number of relevant items. We will denote by capital R the set of ranks of those items. For example, if these are the items presented to the user, and the user clicks on the items highlighted in green, then the set of ranks would be 2, 6, and 8. Now, most common metrics can be defined as a function of this capital R. For example, precision at k is given by this expression, and this corresponds to the number of relevant items ranked in the top k divided by k. Now, this defines a metric for a given query X, and then the metric is average over X in some dataset. Okay, let's define sampled metrics. Because the number of items can be very large, during evaluation, a common practice has been to only rank a subset of the items, which consists of the relevant ones, together with a random sample. Let's look at an example. Suppose that the relevant items are the ones highlighted in green. So if we were to rank all items, the exact ranks would be 6, 8, and 17. But instead of ranking all of the items, we take the relevant ones, together with a random sample, highlighted in orange, then use the algorithm to rank this subset. The resulting ranks in this case would be 2, 3, and 6. Let's call the set R tilde. The common practice is then to report the metric applied to R tilde instead of R. Now, clearly, the sampled ranks R tilde underestimate the true ranks R because of sampling. However, when we compare two recommendation algorithms using the same procedure, it is a valid question whether or not the relative order of the algorithms is preserved. It's worth mentioning here that sampling is common both during training and evaluation of recommender systems. It is well studied for the training part, but the effect of sampling is not well understood for evaluation, and this is the subject of our study. Let us now focus on the case when there is a single relevant item per user. In this simplified setting, we can derive closed-form expressions and clearly highlight the effect of sampling. The exact metrics can be written as a function of the rank R of the relevant item. Here's a couple of examples. AUC is a linear function of R. Precision at k and recall at k in red and purple are step functions. So they assign a constant weight to all of the ranks up to k, and then 0 weight to all other ranks. And NDCG and average precision are also decreasing functions of the ranks. One decreases as 1 over log R, and one decreases as 1 over R. Note that by design, every metric is non-increasing in R, and all of them, except AUC, focus on the top ranks. We can also derive closed-form expressions for the sampled metrics. Let's assume that the items are sampled uniformly, which is common in practice. Then the probability that the random item is ranked better than the relevant item is R-1 over N-1. On this figure, this corresponds to the proportion of items on the left side of the relevant item. Now, when we sample m times, then the measured rank R tilde is simply the number of successes plus 1. For example, in this case, There are 2 samples that fall on the left side of the relevant item, so the rank is 3. In other words, the measured rank R tilde follows a binomial distribution with parameters that depend on the sample size M and the true rank R. Because we know the distribution of R tilde, we can calculate the expected metric under sampling. Here's an example applied to recall at 5. In purple is the exact metric, which is a step function as we saw earlier. Under sampling, the expectation of the sampled recall is still a decreasing function of R, but the rate of decrease becomes much slower as the sample size decreases. Here the red curve corresponds to sample size M equals 1,000, green corresponds to 100, and orange corresponds to 10. One property that this plot highlights is the fact that the bias of the estimate depends on the true rank. And because different recommendation algorithms may have different distributions of the true rank, the bias will in general depend on the algorithm being evaluated. For this reason, common metrics such as precision, recall, NDCG, and average precision are not consistent with the exact metric in expectation. AUC, however, is consistent because it's a linear function of the rank. Next, I will give a concrete example on the MovieLens dataset. This is an experiment on MovieLens 1 million, which consists of about 6,000 users and 3,500 items. The protocol is to hold out for each user the last relevant item or the last interaction for evaluation. We trained and evaluated 3 recommenders. The particular algorithms do not matter for the purpose of this experiment, so I will simply call them X, Y, and Z. The goal here is not to make a statement about the quality of the algorithm, but rather about the evaluation protocol itself. Here's the distribution of the true ranks for each of the 3 algorithms. As we saw earlier, when the distribution of true ranks changes, the bias of the estimate may change in such a way that the metric becomes inconsistent under sampling. In this experiment, we will verify that this is indeed the case in a real application. Let us look at recall at 10. Here, we plot the expected recall as we vary the sample size M. Depending on the sample size, different conclusions can be drawn. When the sample size is small, we conclude that in expectation, X is better than Y better than Z. Then, as we increase the sample size, the order of Z and Y is reversed. Then the order of Z and X is reversed. And finally, we get to the correct order when the sample size is more than 1,000. This corresponds to about a 25% sampling rate. Note that the plots here show the expectation of the sampled metric. One may wonder whether the variance is high for small sample size, which might help us avoid making false conclusions in practice. So let's take a closer look at sample size M equals 100. It turns out that the variance is in fact quite low. So even if one were to repeat these measurements multiple times, the same wrong conclusions would be reached. In other words, sampled metrics are high bias, low variance estimates of the exact metrics, unless the sample size M is very large. This raises a natural question of whether a better estimate can be designed. This is what I will discuss in the next section. As we saw earlier, the typical procedure is to measure the sampled rank R tilde and then report M of R tilde. And we saw that this is in general a poor estimate of the exact metric M of R. Instead, we can define a new function, M hat of R tilde, that can be a better estimate of M of R. The first simple correction one can make is to use an unbiased estimate of the true rank instead of the observed rank R tilde. This is easy to implement. It just consists of an affine scaling of the measured rank before applying the metric, and is given by this expression here. In our experiment, this simple correction already gives some improvements. Another correction method is to minimize a bias-variance trade-off. This can be done by solving the following optimization problem. Remember that our goal is to define a function m hat of r tilde, but because r tilde can only take discrete values between 1 and m plus 1, this is the same as choosing a vector in Rm plus 1. Next, we want to choose the vector that minimizes this objective, which is a linear combination of squared bias plus variance. As a function of the vector m hat, this is a quadratic function, which makes this problem easy to solve. For example, the expectation term is given by this expression, where we saw earlier that the probability of r tilde given r is given in closed form. So this is a binomial distribution with known parameters. And the same applies to the variance term. There are a few parameters that can be adjusted in this problem. First, if a prior on the rank distribution is available, it can be used here, although in our experiment we use a uniform prior. Finally, the parameter gamma controls the trade-off between bias and variance. In particular, setting gamma to 0 defines the minimum bias estimator. But this typically has very high variance, at least in our experiments, which makes it mostly unusable in practice. So we recommend using a non-zero value for gamma. Now, let's revisit the same movie lens example with correction. So here again, we plot the expected recall at 10 as a function of the sample size. Notice that here too, the expected order changes as we increase the sample size. However, in this case, it only takes about 60 samples to get the correct order compared to 1,000 samples without correction. Once again, let us take a closer look at sample size n equals 100. In this table, we repeat each measurement 100 times and then count how many times the order is correct for each pair of algorithms. This allows us to take into account the variance and not just the bias. For example, this number here means that the sampled recall gave the correct order for x versus y in 0% of the repeated measurements. Similarly, this number means that the correct order is obtained in 31% of the measurements. Okay, the first column here corresponds to the sampled metric without correction. As we have seen earlier, the variance is low, so the measurement is either always right or always wrong. Notice that AUC is consistent under sampling, but in the majority of cases, the sampled metric gives the wrong conclusion. The second column corresponds to the simple rank correction, which consists of using an unbiased estimate of the rank. This already provides a significant improvement. The remaining columns correspond to the bias variance correction for different values of gamma, ranging from 1 to 0.001. Theoretically, as gamma decreases, the bias should decrease and the variance should increase. In particular, when gamma is equal to 1, it appears that the bias becomes too high and we get the wrong conclusion for comparing x versus y. On the other hand, when gamma is too low, the variance increases and the quality of the estimate starts to degrade for all pairs. In this particular example, it seems that gamma equals 0.1 gives the best overall improvement. But of course, the optimal value of gamma depends on the particular problem. To conclude, with this work, we wanted to bring attention to the potential danger of sampling during evaluation. Many of the common evaluation metrics have high bias and low variance, and this could lead to apparent confidence in the wrong conclusion. For this reason, we recommend avoiding the use of sampling during evaluation, or using a sample size as large as possible. When sampling is unavoidable, the correction methods that we propose can give an improvement, although they are not completely immune to this issue. For additional details, we invite you to read our paper on sampled metrics for item recommendation. Thank you for watching.